So, hi everybody. This talk is a follow-on that focuses on how we tuned performance for the solution that we presented at last year's Chapel conference. I'm going to start with the end goal. So, the challenge that we talked about last year was if we use Chapel and fabric attached memory, which we call FAM, how quickly could we simultaneously ingest and interactively process, so simultaneously ingest and process data using a cluster of nodes, a small cluster of nodes. And for this, we use the Arcuda framework for interactive data analytics. So basically, Arcuda lets data analysts use APIs from familiar Python libraries such as Pandas and NumPy to interactively explore and manipulate very large data sets. And Arcuda uses a client-server model. So the Python program acts as a client that connects to an Arcuda server. The Arcuda server is written in Chapel, so the actual data processing is done using Chapel on the compute cluster. And we used OpenFAM, the open source project OpenFAM, to expose memory from a number of nodes as a pool of fabric attached memory to the Arcuda server. So the Arcuda server acts as an OpenFAM client with our solution. So one challenge that we address is that when you have long-running jobs whose resource requirements vary over time, sizing becomes an issue. As I said, the Arcuda server is a Chapel program, so similar how it is difficult to add and remove nodes resources from a running MPI or SHMEM program, you need to decide how many nodes to allocate to an Arcuda server when you start it. The challenge is that, especially for interactive jobs, the resource requirements can vary greatly over the lifetime of a long-running job. So, and therefore, there isn't necessarily a right answer to the question of how many resources should you allocate right off the bat. So, for example, in the picture here, you can see that a job might at some point need to process a great deal of data, symbolized by the giant wheelbarrow. But then later on, it might not require so many resources because it might have narrowed down the data and the person wants to work on a smaller data set. So if they allocate too many nodes, they're going to be underutilizing nodes and your cluster is not going to be fully used. And if they don't allocate enough nodes, they might run out of memory. So that's how this is related to a concurrency problem. Okay, so our approach to addressing this challenge was to use Arcuda and FAM to build a Python dataset management application. And this application, this dataset manager, lets analysts use Arcuda to interactively explore continually ingested datasets stored in FAM. So basically, the dataset manager organizes discrete batches of data that are ingested, and it puts these batches into logical datasets that grow over time as more data is ingested. Like an Arcuda Pandas or Pandas data frame, a data set consists of an index plus optional column data. And as the ingested and derived data is, as ingested and derived data sets are processed and stored incrementally in FAM, then the programmer can derive further new derived data sets and new derived columns by applying operations such as filter, scatter, gather, and sort onto those data. Once stored in FAM, these data sets can be shared with other programmers and used to speed time to results for future operations. And they can also be automatically updated by workers. And we think that this approach of offloading opens the door for suspend and resume and recovery from failure. This slide illustrates how OpenFAM helps the dataset storage manager page batches of data from FAM into Arcuda PD arrays, which are which are Chapel arrays on the servers. And the goal here is to get efficient local processing. So remember that the Arcuda server acts as an OpenFAM client. So the figure is showing an OpenFAM client performing a gather operation that uses RDMA to copy values from an array of data stored in the memory of a FAM server into the local memory of a compute node. That's what this slide is showing. So this slide lists some other things we did to improve performance beyond extending the FAM dataset manager to use work stealing, like I described 2 slides ago. I'm just going to run down them. So first off, we had 2 NICs on every node. So to take advantage of that, we bound a locale, a chapel locale of the Arcuda server to each socket plus a NIC. Second, OpenFAM supports atomics on remote fabric attached memory. So we were able to coordinate workers and data processing without using locks. And note that OpenFAM also does support locks. Third, we registered the chapel memory with OpenFAM's libfabric endpoints so that all the memory within every chapel locale was pre-registered for RDMA. And then finally, this is not really a chapel optimization, but we updated OpenFAM to use Mochi Thallium instead of gRPC for communicating between the OpenFAM servers and clients. Remember that the Arcuda server is acting as an OpenFAM client. And so this slide shows a breakdown of where the time went when we ingested data using 20 chapel locales. And basically what this is doing is it's showing the impact of switching to Mochi Thallium. So the graph on the left shows the latency of ingesting 8 terabytes of data on 20 chapel locales. So the problem we had found was that gRPC scaled poorly as we increased the number of locales, the number of OpenFAM clients. So it was a bottleneck. Those green bars you see on the left started off really little, like the bars on the right, but they got bigger and bigger as we added more and more clients. So we switched to Mochi Thallium, and then the bottleneck went away, and there you see the result where with the same number of locales, now the initialization is no longer, the pre-creation of the FAM arrays is no longer the bottleneck. Okay, oops, wrong direction. You might be thinking, okay, after all that, show me the performance of the actual ingest and work. So this slide shows the isolated ingest performance from ingesting 8 terabytes and 16 terabytes of data while varying the batch sizes. Because we wanted to focus on data movement and compute times as opposed to file system I/O, because we're trying to show the benefit of the in-memory data, we used generated data based on the New York taxi cab data set. This slide shows that with a 40 gigabyte batch size and in isolation, meaning that ingest is the only thing running, we could ingest 16 terabytes of data in about 41 seconds. And to put the throughput numbers, which you see on the left, in perspective, the measured unidirectional bandwidth was about 24 gigabytes per second per NIC, or a total of 480 gigabytes per second to and from the FAM nodes. Okay. Slide 9, this one. Okay. This slide shows isolated data processing performance for 8 terabytes and 16 terabytes of ingested data. So this means the data is already being ingested and we run the workers and they just process it all. I'll show you the actual workflow that's being done here at the end of the talk. But basically, the data analyst executes a number of operations on the ingested data, producing about 21 derived data items. And in order not to be bound by a human being's typing speed and thinking time, we actually implemented the interactive workload as a Python script. The numbers on each bar are in the backup slides if anybody really wants to see them, but the highest throughput number on the left, the big purple bar on the left, is about 437 gigabytes per second. And the lowest latency number, the little purple bar on the right, is about 37 seconds. And this is, again, in isolation. Okay, so now we're on to simultaneous ingest and processing. So this slide shows the numbers for that. And by this, we mean that the data analyst is executing the operations, manipulating the data at the same time that the data is being ingested. So the data is growing as the workload goes on. And as you can see here, the numbers are lower but that's because we're now having bidirectional traffic. We're writing data to the FAM and we're reading it at the same time. And to put these numbers in perspective, the measured bidirectional bandwidth is a total of about 340 gigabytes each way. So we get, as you can see on the right, left-hand side, about 226 gigabytes per second at best. And we can do the simultaneous ingest and workflow in about 70 seconds. Okay, we have about 3 minutes left. So I do have time to do this, okay. I'm going to show a trace-driven animation next of simultaneous ingest and continuous processing. And this slide shows the setup for that animation. Basically, there's 20 ingest locales, which are Chapel programs, running on 10 nodes, and there's 64 asynchronous workers using our CUDA running on 32 nodes, one per socket, pinning locales to sockets and NICs. And the interactive workflow is the one I showed earlier, creating the 21 derived pieces of data. Okay, so here we go. Let's see what this goes. Okay, so this slide is animating what happens when batches of data are ingested. The blue lines you see on the left are showing how many batches have been ingested so far. There's going to end up being 1,600 batches in total. This is for 16 terabytes. It's an animation that's working in real time. Basically, we sampled the number of batches that had been ingested for each of these 21 items 10 times a second. Each row shows a different data set or column. The first ingested data set for space reasons, I didn't show all the columns. It just shows up as the one ingested data row. And every row underneath that shows like a derivation chain. So the analyst filtered out the most expensive rides in that filter data set, and then they did a bunch of gathers to gather the column data. Oh, look, it finished already. To gather the column data for each of those most expensive rides, and then they sorted the runs for the filtered data set, and then they gathered using that sort index all the relevant column data for each column, the pickup zone, drop-off zone, pickup time, drop-off zone, and fare fields, and then they did the top 10 of that, and then did the gathers for all the attributes, and then finally they did a full sort. So now I'm at the end of the presentation, and I'm open for questions. I will leave it on this backup slide that shows a summary of the data management approach, because I think that was a little bit rushed.
Yep. Thank you, Harumi. Does anyone have any questions? Okay. You want to go ahead, Brad?
Yeah. I first have kind of a nuts and bolts question, which is, so what you're doing, I think if I got all your numbers right, is very similar to the co-locales in terms of like multiple Chapel processes or locales per node. But if I remember correctly, I think you started this work probably before the co-locales were coming online. And so have you done sort of something homegrown there, or have you managed to switch over to the co-locales?
We have not switched over to the co-locales.
Okay.
And here you mean especially how we're bringing up 2 locales per node so that we can pin one to each. Yes.
Yeah.
We did this work last fall, summer and fall, and yes, we're very interested in the new co-locale work.
Okay. And again, that was just sort of a nuts and bolts thing I was curious about. As a slightly maybe more interesting question, I hope it doesn't come off as a challenge. It's not meant that way.
Good.
Let's say that I had a system that I didn't have FAM on, but I had, say, like SSDs on every node or some other kind of storage solution. What elements of the work you've done here would translate? And what elements would be like, oh, well, because you don't have FAM, you're missing this feature or this nicety, and therefore you wouldn't be able to recreate this sort of approach?
That's a really good question. Yeah, that makes total sense. And it's one that we're actually very interested in exploring. So FAM, although it says memory node down here, these are just conventional nodes that are exposing their memory. So, so if you had SSDs, first of all, I think the the big difference between SSDs and a node that is exposing its memory for use over RDMA is the bandwidth and the latency, because SSDs bandwidth and latency just don't compare to memories. It's like what? I'm not going to say a number because I'm going to make a mistake and say the wrong number, but it's lower bandwidth and higher latency. Still, someone might consider letting nodes share memory on other nodes, even if those other nodes are not dedicated completely to running a memory server. And we are very interested in that. So that's one thing. The second thing is the idea of having a pool of work and letting work migrate between our CUDA servers really helps with the sizing problem. And this is probably not an issue if you have a very uniform workload that is extremely predictable and maybe even short running. Like if you know for sure that you're going to need 100 nodes to run this job, and it's going to be using those 100 nodes just pegged the whole time, well, then you perhaps don't need this solution for that. It's more useful if you're going to be sharing a cluster between like a bunch of different people, and the different people are going to be running like more interactive or more variable workloads in terms of like their requests. And then this offloading model makes more sense, if that makes sense. There's possibly also something with memory registration that people should, well, actually that might be, actually forget I said that one, because Chapel registers its heap. So that's okay, forget I said that one.
Okay. All right, great. Thanks very much for that answer. That's really helpful.
Any final questions for our speaker? So if not, that wraps up this session. Thank you.
Okay, thank you.